EDX Core Pure, complex numbers 2, the Argand diagram. Introducing the Argand diagram and representing addition and subtraction. How do we form the Argand diagram? Geometrically, what happens when 1 is multiplied by minus 1? We know that when we multiply 1 by minus 1, we get the answer minus 1. So the number 1 on the real axis becomes minus 1. So multiplying by minus 1 has produced a 180-degree rotation about the origin. What might happen if we multiplied instead by the square root of minus 1? Would that produce a 90-degree rotation about the origin? And indeed it does. 1 times the square root of minus 1 does produce a 90-degree rotation, and 1 times I gives me I. So multiplying by I has produced a 90-degree rotation about the origin. So we now have the real axis where all the real numbers are that you've used previously, and we now have a perpendicular imaginary axis, and we have the two-dimensional complex plane. So if we consider the complex number z1, which is 3 plus 4i, this can be represented by a single point on the Argand diagram with coordinates 3, 4. Or it can be represented by a line joining the point from the origin, rather like a vector. If we consider the complex number z equals 4 plus I, which we can see on the diagram, the complex conjugate would be z star equals 4 minus I. What do we notice about the relative positions on the Argand diagram? Well, we can see that z star is a reflection of z in the real axis. Is this generally true? Yes. Z and z star will always be mirror images of each other in the real axis. We can now think about adding complex numbers and what that would like geometrically. So here we've got z1, which is 2 plus 5i, and z2, which is 5 plus I. So if we consider z1 plus z2, we'd be looking at 2 plus 5i, and we're going to add on 5 plus I. And we've seen previously how we can collect like terms, like the real terms. So we've got 2 plus 5 is 7. And if we collect the imaginary terms, we've got 5i plus I is 6i. So z1 plus z2 is 7 plus 6i. So geometrically, there is z1 shown as a directed line from the origin with coordinates 2, 5. There's z2 shown as another directed line from the origin with coordinates 5, 1. And there is the answer z1 plus z2, so that's 7 plus 6i. So that's a directed line from the origins called z1 plus z2. If we can treat the complex numbers like vectors on the Argand diagram, then the diagram could be represented like that. We could show z1 as a directed line from the origin followed by z2. So we've got z1 followed by the z2, and we can see the answer is given geometrically as the direct line z1 plus z2. Likewise, we can look at subtractions. So we're going to take z1 from z2. So this time we're going to do z2, take away z1. So that's 7 plus 6i. And we're going to take away 2 plus 5i. Be careful with the subtraction. So looking at the real parts, we've got 7 take away 2 is 5. And looking at the imaginary parts, we've got 6i take away 5i is just plus 1i. So z2 take away z1 should be 5 plus I. Again, this can be represented on the Argand diagram. So there is our starting point, complex number z2, a directed line from the origin with coordinates 7, 6. And there's another directed line from the origin with coordinates 2, 5, but we need to show Z2 take away Z1. So at the end of Z2, I'm going to add on the vector called minus Z1. So this is now showing Z2 followed by minus Z1, which is the same as Z2 followed by Z1 pointing in the other direction. So this diagram now is showing Z2 followed by minus Z1, and the result of that is the purple vector 5 plus 1i. So in the next session we'll be going to look at representing rotation and the effect of multiplying by I.